In this lecture, we're going to talk about a special exponential function that we refer to as the natural exponential function. And to motivate the idea, we're going to start with a scenario that seems a little bit strange, really unrealistic, but I'm hoping it will help you see where this base naturally occurs. So we're going to look at this scenario where we're investing just $1, and we're going to get 100% interest on our investment, and we're going to see what happens over 1 year when we let the number of times we compound vary. So we're going to look at different scenarios for the number of compounding periods. First, let's talk about what the model would be for this. We know that when the interest is compounded a finite number of times, we use the model A equals P times 1 plus R over N to the NT power. A is unknown. The principal is just $1. The interest rate is 100%, which as a decimal would be represented by 1. N is X. We're letting the interest be compounded X times per year. And T is 1 year. So substituting this in, we get A equals 1 times 1 plus 1 over X to the X times 1 power. And if we simplify that, multiplying by 1 here doesn't change anything. X times 1 is just X. We get the model 1 plus 1 over X to the X power. What we're going to do is investigate how this function grows as we increase the number of compounding periods. We've seen before that the more times you compound per year, the more money you make in the end. But what we're going to look at is whether or not that growth is unbounded, or if there's some sort of cap to the maximum amount of money that you can make based on the number of compounding periods. So I've already put this function in the calculator, 1 plus 1 over X to the X power. And now we're going to go to the table and look at some different compounding periods. And for the first couple, we can anticipate what the answer is going to be. For example, if the interest is compounded annually, just one time per year, well then our dollar sits in the account for the entire year, and then at the end of the year they give us 100% interest. So they give us another $1, so we have a total of $2. The total value is 2. If we compound semi-annually, then after 6 months, they'll give us 50%. Remember, they're going to cut that 100% in half. So they'll give us 50% of our investment. Well, that's 50 cents. So now we have $1.50. Then that $1.50 sits for another 6 months, and then they give us another 50%. Well, 50% of $1.50 is 75 cents. So now we have $2.25. So you can see that the model's working. It gets harder to guess at what the balance is going to be when we increase the number of compounding periods. Like when we increase to 4, after 3 months, they're going to give us 25%, so we've got $1.25. And then after another 3 months, they'll give us 25% of that. Well, 25% of $1.25 is like 31.25 cents. So now we've got $1.56. And then we get 25% of that. You can see this is going to be hard, but you were going to get more money. We wind up with about $2.44. If we increase that to monthly, we get $2.61. Another common compounding period would be weekly, 52 weeks. Now we're up to $2.69. Let's go to daily, 365 times. You can see this is clearly leveling off. This is at about $2.71. And if we raise this to hourly, if we compound the interest every hour for an entire year, there are 8,760 hours in a year. Only due to rounding do we get an extra penny. We're at like 2.7181. And just to be obnoxious, let me go up here, delete an entry, and jump this up to just 1,000,000. So now we've got 1,000,000 compounding periods over the year. That barely changes the output at all. You can see that in this last spot, we've leveled off at what appears to be a 3, but if you look, it's really a 2. It's pretty clear that this function is leveling off at some number. And it happens to be an irrational number. It's a non-terminating, non-repeating decimal. So they had to give it a notation, and we call it lowercase e. We say that as x goes to infinity, 1 plus 1 over x to the x power approaches this number e, and as we saw in the calculator, it's around 2.718. That's a pretty good estimate. When I think of the value of e, I think of about 2.7. The same way that we estimate pi. When you think of pi, you probably think of around 3.14. That's the most common way to estimate pi. When I think of e, I think of a number that's really close to 2.7. As we saw, this base e naturally arose in this scenario, and it turns out that this number e pops up in all kinds of places. It's considered one of the most important constants in all of mathematics. Because this base e pops up so much, we call the exponential function with base e the natural exponential function. The natural exponential function f is defined by f of x equals e to the x, and again, think of e as just some number close to 2.7. Let me show you some values of e to the x. If we let f of x equal e to the x, then f of 0 would be e to the 0 power. And it doesn't matter that e is this weird number. We've learned that any non-zero base to the 0 power is 1. So f of 0 is 1. This shouldn't be surprising. All exponential functions have a y-intercept of 0, 1. This is no exception to that. F of 1 is equal to e, because when we plug 1 in, we get e to the first, which is e, and that is approximately 2.7. The actual value is e. The approximate value is 2.7. F of 4 is equal to e to the fourth. Now, I don't know what e to the fourth is, so I'm going to go to my calculator here. And e is such an important constant that there's actually a spot on your calculator for raising e to a power. If you look above this ln key, in the same color as your second key, there's an e to the x command. In fact, e shows up on the face of your calculator twice, once here and also above the obelisk key above the division key. Math nerds like to argue about whether e or pi is the cooler number or the more special number. Well, one argument in favor of e is that it's important enough that it's got 2 spots on the face of our calculator. Stupid pi's only got 1. Anyway, let's raise e to the fourth power. I'm going to push the second key and then this ln key. And in the newer calculators, you'll actually get a superscript that you can type in. In the older calculators like mine, you get some parentheses that you can type the exponent in. Our exponent is 4. And we hit enter. And e to the fourth is around 54.6. So f of 4 is equal to e to the fourth. That's approximately 54.6. F of negative 1 would be e to the negative 1 power. And that's the same as 1 over e. Remember that a negative exponent is a reciprocal. Here we're taking the reciprocal of e to the first, so we get 1 over e. To get a decimal approximation for this, we actually have 2 options. I can use that same process of raising e to a power and type negative 1 in. Gives us around 0.37. Alternatively, we can do 1 divided by e. If you just want to raise e to the first power, you can hit second and that division key, the obelisk key. And again, we get around 0.37. So again, e is just a number. It's not a very nice number. It's what we call an irrational number because it's a non-terminating, non-repeating decimal, just like pi. At this point, I can't help but bring up the fact that e and pi have this weird relationship with one another. There's this formula that math nerds love. If you ever go to a bar that's frequented by math geeks, this is guaranteed to be graffitied somewhere in the bar. But if you take the base e and you raise it to the I times pi power, so pi is that 3.1415926 that's related to circles and lots of other things, and I is the square root of negative 1 that we talked about earlier in the course. And you add 1 to that, you get 0. And math geeks just think this is the most beautiful thing that's ever happened. You've got 5 of the most important constants in all of mathematics related in this simple equation. And it's not that some dork decided that this should be true. Somebody proved that it is true. This isn't a particular fact that we're going to use in our class, but every time I introduce E, I have to bring this fact up because this is just the most beautiful thing that ever happened in the history of ever. This is number 1, and then well below that is the birth of my kids, that's number 2, and then the Mona Lisa or whatever. But this is clearly the most gorgeous thing that's ever happened. Anyway, let's look at the graph of f of x equals e to the x. I claim you should already have a vague notion of what this looks like. We already know what exponential functions look like. This base is bigger than 1, right? This base is around 2.7. All exponential functions with a base greater than 1 are of that increasing type, going through the point 0, 1, leveling off at the x-axis on the left side, and shooting up towards infinity on the right side. Our data here suggests that this is true. We can see that f of 0 is 1. We see that f of 1 is around 2.7, and f of 4 is already up near 55. So this function's growing very quickly on the right side, and on the left side it's leveling off, getting closer and closer to 0. Using that, we can sketch other graphs, assuming that they fit those transformations that we're familiar with. Like here, let's look at the graph of f of x equals e to the minus x plus 3. Well, we already know what e to the x looks like. It's that increasing exponential graph that goes through the point 0, 1. The minus x is a reflection over the y-axis. That's a horizontal reflection. So now it's going to point in the opposite direction. And then the plus 3 is going to move all those points up 3 units. So where this graph would normally go through 0, 1, we're going to shift that up to 0, 4. Where this graph normally increases, we're going to flip that to decreasing. And one other thing we want to consider, the horizontal asymptote is usually on the left side at y equals 0. Now we've flipped it and shifted it up 3 units, so it's on the right side at y equals 3. So the graph is going to bend in like this and level off at y equals 3. Back to our graph v to the x, let's highlight some of its characteristics. We've listed these in general, but it'd be a good review. The domain of this function is all real numbers. The range, however, is restricted. We mentioned this in general before, but in particular for e to the x, notice that all of the outputs are positive. We're going to use this fact in a little bit, which is one of the reasons why I want to bring this up. It's got a y-intercept of 0, 1. We already talked about that. It's an increasing function over its entire domain. And one important thing about that is that that means that the function is 1 to 1. Again, we already argued that all exponential functions are 1 to 1, but this one is in particular. And we've been using that fact to help us solve equations, and we're going to do that here too. Here's an example. Let's solve the equation e to the 5x squared plus 3 equals e to the x squared minus 3x plus 13. Well, since f of x equals e to the x is a 1-to-1 function, the only way that these two outputs could be the same is if the inputs, the exponents, were the same. So we're going to start by setting the exponents equal to one another. 5x squared plus 3 is equal to x squared minus 3x plus 13. This is a quadratic equation, so we probably want 0 on one side. I'm going to subtract x squared, add 3x, and subtract 13 from both sides. Collecting our like terms, we get 4x squared plus 3x minus 10 equals 0. By getting 0 on one side, we've opened up the avenue to the quadratic formula, but we can also try factoring, and it turns out that this one factors. I'd like you to try to factor it. Please pause the video and see if you can get that factored. It's good practice. A lot of people would start with the assumption that we want to break 4x squared into 2x and 2x, but you can tell that's not going to work because the middle term was odd. If we break this into 2x and 2x, that guarantees an even middle term, so the only reason we'll guess is 4x and x. Now we need two numbers that multiply to 10. Most of us would try 5 and 2. Putting the 5 on the right doesn't seem very smart because 4 times 5 would give us 20. So we'll try to 5 over here and the 2 here. And let's see, that gives me 8x on the outside and 5x on the inside. If I get positive 8 and negative 5, then I get the 3x in the middle, and negative 5 times negative 2 would give me negative 10. So this equation has two solutions, x equals 5/4 or x equals negative 2. We wouldn't do this any differently if the base had been 2, or if the base had been 7, or in fact any positive number not equal to 1. This isn't an exponential equation. I've just used e as part of the coefficient of the variable. We're going to solve this equation for x. It says 2ex plus 5 equals 11. Well, if this said 2x plus 5 equals 11, you wouldn't hesitate. You'd subtract 5, you'd divide by 2, that solves for x. Same idea here. We're going to subtract 5. We get 2ex equals 6. And we divide by the coefficient, which is 2 times e. 2 times e is just a number. Since e is around 2.7-ish, 2e is around 5.4. It's a little bit bigger than 5.4. So this is x equals, We can in fact cancel a factor of 2 here and we get 3 divided by e. That number is just a little bit bigger than 1. One thing I want to point out, this is the answer. If you want to approximate it, you can. 3 divided by e, again, is a little bit bigger than 1. It's around 1.1. But that's not the answer. That's just an approximation. The answer here is 3 divided by e. That's the exact solution. 1.1 is just an approximation to that solution. Okay, so those are equations similar to things we've done before. Let's look at a new kind of equation. We're going to solve this equation for x. It says 30x e to the 5x plus 6e to the 5x equals 0. And what we typically try to do when we get 0 on one side is factor. Now the kind of factoring I'm talking about isn't the guess and check style factoring that we did a couple of problems ago. Here I mean pulling out GCFs. We can pull out the GCF. Both of these coefficients are divisible by 6, and they both have an e to the 5x. So the greatest common factor is 6 times e to the 5x. When we pull the 6e to the 5x from the first term, it leaves behind a factor of 5, because 6 times 5 is 30, and it also leaves behind this x. When we pull 6e to the 5x from itself, it doesn't leave a blank. That's a common mistake I'll see students make, is they'll write this. But that's clearly not equal to the original problem, because if I were to multiply this together, it would only give me the first term. When we pull 6e to the 5x from itself, it leaves behind a 1. Think of it as a division step. We're dividing this term by itself. Well, when you divide a non-zero expression by itself, you get 1. We've seen equations like this before, again, not with exponential expressions floating around, but we have this zero factor principle that says that when you multiply two things and you get 0, then one of them had to be 0. So either 6e to the 5x is equal to 0, or 5x plus 1 is equal to 0. Now this second one is easy to solve. Subtract 1, divide by 5, we get x equals negative 1/5. The first one, I guess we could divide both sides by 6, get that out of the way. We get e to the 5x equals 0. And now the question is, how do you solve this? Well, you can't. This says that e to some power is going to be equal to 0. Well, if you go back to our properties of e to a power, we said that e to a power is always positive. The range is from 0 to infinity, not including 0. E to a power can never be equal to 0. This part has no solutions, and so the only solution is x equals negative 1/5. Some of you might know another way to show that e to the 5x equals 0 has no solutions using logarithms, but we're not there yet. So our argument will be, well, e to a power has to be positive because the range of the graph of f of x equals e to the x is 0 to infinity, not including 0. Let's try another one like that, but with a little bit more work to it. This says 2x e to the negative 2x minus 4x squared e to the negative 2x equals 0. And before I continue, I want to point out that these equations aren't completely contrived. Each of these would be the result of some calculus steps. There would be a calculus problem that would involve stuff like this. So those of you headed to calculus will see this in the future. To start off, I want to try factoring, and I can't factor in the sense of breaking this into two binomials, but I can pull out the GCF. Both terms have a factor of 2, both terms have at least one factor of x, and both terms have a factor of e to the minus 2x. So the GCF is 2x e to the minus 2x. I want you to pause the video and see if you can come up with the other factor. When you pull 2x e to the minus 2x from itself, it leaves behind a 1. I hope you didn't forget that 1. When you pull 2x e to the minus 2x from minus 4x squared, you get a minus 2. Negative 4 divided by 2 is negative 2. And you're also left with an x, because x squared divided by x is x. We pulled out the e to the minus 2x. So we have 2x equals 0, or e to the minus 2x equals 0, or 1 minus 2x equals 0. 2x equals 0 has a solution, that's x equals 0. 1 minus 2x equals 0 has a solution, that's x equals 1/2. The middle equation has no solution. E to a power can never be equal to 0. It doesn't matter that the exponent is negative. In fact, that makes the argument even easier to make. E to the negative 2x means 1 over e to the 2x. Well, this fraction can never be equal to 0 because the numerator is stuck at 1. That equation doesn't have any solutions. So the two solutions are x equals 0 and x equals 1/2. One more. This is again the result of a real calculus problem. In fact, this one used a function that is important in statistics. This equation says e to the minus x squared minus 2x e to the minus x squared equals 0. See if you can get that factored. Okay. Unlike the previous problems, we can't pull out any coefficients, but we can pull out an e to the minus x squared. When we pull that from the first term, it leaves behind a 1, and when we pull it from the second term, it leaves behind a minus 2x squared. So we have e to the minus x squared equals 0, which we know doesn't have any solutions. When you raise e to a power, you can't get 0. We also have 1 minus 2x squared equals 0, and that doesn't factor in the traditional sense. You can factor it using radicals, but perhaps an easier way to do this would be to add 2x squared to both sides, divide by 2, and then use extraction of roots. So we get x equals plus or minus the square root of 1/2. It's perfectly acceptable to leave your answer like this. But for those of you that can't help yourselves, this would be plus or minus the square root of 2 over 2. We talked about the graph of e to the x. We solved some equations that involve e. And of course, we brought up this beautiful formula, which again has nothing to do with our class. But come on, look at it. It's just so awesome. If you have any questions about any of the topics in this video, don't be afraid to reach out. You can see me in an office hour, or you can send me some emails.